All right, welcome back to Deep Dive. Today we're taking a look at something pretty cool, I think. It's called RWKV-7, also known as Goose. We're gonna go deep on this one. It's all about those AI models that can really understand and work with sequences of information like language.
Yeah, exactly. You've brought the technical paper on RWKV-7, and it's really interesting stuff. It really takes a new approach to sequence modeling. And for our listeners out there, we're going to try to break down the core innovations here. We want to see what really makes this RWKV-7 tick, especially how it updates its internal state as it's processing data, how it evolves, and how that impacts its computational power. This is like a peek into the cutting edge of AI research.
So, okay, the paper says that RWKV-7 is built on this delta rule for update date. Now, for those of us who may not be experts in AI theory, can you maybe give us a simpler explanation of what this delta rule is all about and how this RWKV-7 takes it to the next level?
Sure. So, at its core, the delta rule, it's like a fundamental learning mechanism. You can think of it like a student who's learning from feedback, right? The delta is like the difference between the student's answer and the correct answer, and they adjust their understanding based on that difference. So in sequence models, this rule is all about how the model's, internal memory or its state is modified as it encounters each new piece of information in the sequence. And what's really exciting about RWKV-7 is how it generalizes this idea. See, previous methods, even, things like RWKV-6 and a lot of linear attention mechanisms, they often used single numerical values or scalars to control how much that state is updated, and the rate at which learning happens.
So it's like a single knob controlling the adjustment.
Yeah, exactly. But what RWKV-7 does is it introduces these vector valued gating and in context learning rates. So instead of just having one knob, like a math volume control, think of it as having multiple knobs, right? Like one for each different aspect or channel of the model's internal state. And this gives you a much finer control over which information is being updated and by how much. And on top of that, they've relaxed the rule for how new information replaces the old information in that state. So it gives you more flexible ways to manage the model's memory. It can even uh, it can even allow the model to use different criteria, like different keys, for deciding what to forget and what to remember.
And this is where things start to get really interesting, right? The paper talks about how RWKV-7's transition matrix, which is like the mathematical structure that governs those state changes, is non-diagonal and input dependent. They say this lets it represent these more functions compared to models with diagonal transition matrices, like a lot of transformers. They even mention computational complexity classes like TC0 and C1. Can you maybe break down what those classes mean and why this is such a big deal that RWKV-7 is different?
Definitely. So these computational complexity classes, they're like ways to categorize problems based on how hard they are for a computer to solve, especially as the input gets bigger and bigger. Models with those diagonal transition matrices, like a lot of those standard transformers, often fall into this TC0 complexity class. And without getting too technical, TC0, it's basically about functions that can be computed with really shallow circuits, even if those circuits are really wide. Now, RAKB7, with its more complex transition matrix, it goes beyond that. It's theoretically groundbreaking because they've proven that RWKV7 with just a fixed number of can recognize all regular languages.
All regular languages. That sounds like a pretty. So, what does that actually mean for RWKV-7 in a practical sense? What are the real world implications of this?
It is a significant advancement. You see, recognizing regular languages, it's a formal way of understanding the ability to keep track of finite states and patterns. So imagine a system that has to follow a strict set of rules or remember a specific sequence of events to figure out the next step. That's what we're talking about here. So RWKV-7, with this theoretical capability, it suggests that it's much better at handling these kind of sequential dependencies and recalling patterns. The paper specifically highlights the ability to do a copy state transition as a key part of what makes this possible. They even show that RWKV-7 can solve an S5 state tracking problem, which is known to be in the NC1 complexity class, which is generally thought to have problems that are more complex than those in TC0, and it can do this with just a single layer. So this really points to a potentially much richer capacity for managing and evolving its internal state compared to architectures that are limited to C0.
So while other models might struggle with certain kinds of, sequence-based reasoning, RWKV7, at least in theory, has more tools in its belt to tackle those challenges. Is that what you're saying?
That's exactly it. It suggests a much more solid foundation for tasks that require keeping track of these complex sequences and those underlying rules that govern them. So it really implies a higher level of expressive power in how it can manipulate and represent information over time.
Okay, so RWKV7, it's not like a completely brand new invention, right? It's built upon earlier versions of RWKV. Can you tell us about some of the main architectural changes they made in this version?
You're right. RWKV7 is an evolution of RWKV6. They've incorporated several really important changes in the architecture to both improve its performance and make it more efficient at processing information. So they made updates to the channel mixing and token shift modules, which are really important for how the model processes and understands the context of the input sequence. One notable change is that they simplified the token shift mechanism. They got rid of its dependency on the input data, which makes processing faster. Similarly, they removed the receptance gating mechanism in that channel mixing module. And again, this was done to improve efficiency. So you can see a clear trend here, right? They're streamlining certain aspects of the architecture to make it faster without losing that representational power.
Yeah, I see what you mean. So by making those basic operations more efficient, they can make the whole model more powerful.
Precisely. Another key change they made was to increase the use of low-rank projections throughout the architecture. Really clever way to balance, the model size, like the number of parameters it has, its processing speed, and its ability to perform well on different tasks. So by using these low-rank approximations, they can reduce the computational costs and how much memory it needs without really limiting the model's ability to learn and represent these complex relationships in the data.
So it's not just theoretical advancements, but also some really practical engineering choices they made in the model's design. So how do these changes actually translate into real results? The paper, it includes benchmark evaluations, right?
It does, and the results are really impressive. So at the 3 billion parameter scale, RWKV7 sets a new state-of-the-art performance on multilingual language understanding tasks. That's a big achievement. It shows just how good it is at processing and understanding different languages. What's really interesting is that it matches the current state-of-the-art performance on English language tasks, but it does it after being trained on way fewer tokens compared to other top 3 billion parameters like Q1 2.5. So this suggests it learns more efficiently and it uses the training data better.
So fewer training examples, but the same top-level English performance and even better multilingual capabilities. That sounds like a big advantage.
It is. They also saw a significant improvement on the MMLU mark compared to RWKV6. MMLU, it tests a model's general knowledge and reasoning abilities across a ton of different subjects. So this improvement means it has a broader and deeper understanding of the world. And then on top of that, on specific multilingual benchmarks, RWKV7 outperforms models like small LM2 and even Llama-3.2. The researchers also tested RWKV7 on internet data that was temporally novel. So that means data that came out after the model was trained. And it did really well even though it hadn't seen as much training data overall. This means it has strong generalization capabilities, meaning it's not just memorizing the training data, it's actually applying what it learns to new information.
Okay, so what about its ability to handle those long-range dependencies? Recalling information in a longer context. How does it do with that?
They tested that with the Associative Recall Benchmark, or AR benchmark, and the results showed that RWKV-7 is really good at retrieving information that appeared earlier in the input sequence, so it can manage its internal state effectively, even over those longer contexts. They also tested it on the Mechanistic Architecture and Design benchmark, the MAD benchmark. This one is designed to really probe the core computational abilities of the architecture, and the results there were also really promising.
So it sounds like RWKV-7 is performing really well across all these different evaluations, especially considering how much training data it's seen. Now, one of the key things about those earlier RWKV models was how efficient they were. So how does RWKV-7 stack up in terms of processing speed and memory requirements?
That's where the RWKV architectures have always been really good. And RWKV7 definitely continues that trend. It keeps those key advantages of using a constant amount of memory and having a constant inference time per token, no matter how long the input sequence is. That's a fundamental difference from transformer-based models. With transformers, both the memory they need and the processing time, it goes up as the sequence gets longer.
Yeah, that consistent time and memory usage, that has to be a game changer for anything that's dealing with really long streams of data.
It is. The paper actually compares the speed of the RWKV7 kernel to RWKV6 and flash attention V3, which is a highly optimized attention mechanism that a lot of transformers use. They have both a faster bfloat 16 precision kernel and a more precise FP32 precision kernel, and they use the FP32 one for training. And the data shows that RWKV7's forward pass, which is the main computation during inference, is it's significantly faster than flash attention V3, especially when you have longer input sequences. Like, to give you a concrete example, they reported inference speeds for a sequence length of 16,000 tokens, and RWKV7's forward pass, without even storing the internal state for backpropagation, only took 7.9 milliseconds.
Wow, that's incredibly fast. So what about memory? How much memory does it need during training?
During training, RWKV7 does need more memory than RWKV6, and that's mainly because it has more variables associated with that, more sophisticated state evolution mechanism and the way it stores that WKV state at certain points. The paper breaks down the number of variables for both models, and you can see that RWKV7 uses more in both the forward and backward passes during training. But this increased memory need during training, it's often a trade-off for those big efficiency gains you get during inference, when you're actually using the model.
Okay, let's dig a little deeper into this state evolution. The paper talks about these state inspections of the WKV state matrices in RWKV7, and they compare it to the earlier versions. What did they find when they looked at that?
This is really interesting from the perspective of model stability. So they found that the WKV state matrices in RWKV7, they have these much smaller root mean square values, or RMS values, compared to RWKV5 and RWKV6. Basically, the numerical values within those matrices are much more controlled. They don't have those large, potentially unstable outliers that you sometimes saw in the previous versions. So this suggests that the model is much more numerically stable during both training and inference, which is really important for reliable and consistent performance.
So it's less likely to have internal computational issues.
Exactly. They also looked at the stable rank of these matrices, which is like a measure of the effective dimensionality or the amount of independent information that's captured in that state. And what's interesting is that RWKV7 actually showed a lower stable rank compared to the older versions when it was dealing with longer contexts. Now, at first glance, this might seem counterintuitive, especially since it does better on tasks that need long-term memory.
Yeah, a lower stable rank, but better long-term memory. It's not obvious how those two things go together.
Right. Well, the researchers think that this actually reflects how much more efficient RWKV7's state evolution mechanism is. It seems like it's compressing information it keeps and using it more effectively. So it's able to hold on to that important information in a more condensed form. So it's not necessarily storing more data, but it's doing a better job of encoding and retrieving the most important information for the task at hand. It's kind of like a really skilled librarian who knows exactly where to find the right book, even if they have a smaller, more organized collection.
Yeah, I like that. It's like more efficient information management in the model's memory. The paper also mentions these ablation studies. What did those experiments show?
Ah, yes. Ablation studies, they're a common technique in machine learning research. Basically, they systematically remove or modify individual parts of the model to see how much each part contributes to the overall performance. So for RWKV-7, these studies showed that using those vector value decay and in-context learning rates that we talked about earlier, they really do help. They also confirmed that it was beneficial to use those separate keys for deciding what information to remove from the model state and what to add to it. So these studies provide evidence that those specific design choices are a big part of why RWKV-7 works so well.
And lastly, the paper talks about this interesting observation about initial token sensitivity, specifically with that endotext special token. What was the main takeaway there?
This was a bit of a surprising finding. They discovered that whether or not that endotext special token was present at the very beginning of the input sequence could actually have a pretty noticeable effect on how well RW7 performed, especially for the smaller versions of the model. So leaving out that token in some cases actually made the performance worse, even impacting the model's ability to remember the very first token of the input.
That's really strange. Why would a specific token at the start have such a big impact?
Well, the researchers believe that this highlights how important it is to properly initialize and set the context for recurrent neural network architectures like RWKV. It seems like that initial token actually helps to set up the initial state and tell the model that a new sequence is starting. What's even more interesting is that they found that using two endotext tokens in a row sometimes made things even better, even though you never see that sequence in the training data. On the other hand, transformer-based models like QN 2.5, they weren't as sensitive to that token, so it implies that they might have better built-in mechanisms for handling the start of a sequence. But the practical takeaway for people using RWKV7 is that it's generally a good idea to include that endotext token at the beginning of your prompts to get the best performance.
All right, so to sum up our deep dive into RWKV7 Goose, it looks like it's a big step forward in sequence modeling, especially in the way it updates its internal state. It uses this generalized delta rule with vector valued gating and flexible state updates, and that gives it more expressive power and a theoretical ability to handle really complex state tracking.
That's right. And we saw how those innovations translate into really good performance on a lot of different language tasks. And it often does it more efficiently with the data. And importantly, it still keeps those remarkable constant memory and inference time characteristics of the RWKV family, which are so important for handling long sequences.
Yeah, and while it may need more memory during training, the efficiency gains when you're actually using it are huge. And those state inspections, they show that it's more numerically stable and that it has a more efficient way of encoding information in its state.
Precisely. Those ablation studies confirmed those core design choices and that sensitivity to the initial token that shows just how nuanced these recurrent architectures can be. So for you, the listener, you now have a much deeper, more nuanced understanding of what makes RWKV7 such a remarkable development in the ever-changing world of AI.
And here's a final thought for you to consider. Think about what these architectures like RWKV7 with their constant memory and processing time could mean for dealing with these truly massive, never-ending streams of data or incredibly long sequences that would just overwhelm those traditional transformer models. This fundamental change in how we manage the internal state of these models, moving toward this more dynamic and adaptable scratch pad instead of just a static cache, it could unlock all these new kinds of applications and maybe even completely change how we approach sequence modeling in the years to come. So thanks for joining us on the deep dive.